Good day, everybody. Thanks for having me. I would like to speak on millisecond pulsar emission mechanisms, and especially on gamma ray and radio pulsars. My name is Christo, and I'm from the Center for Space Research of the Northwest University in South Africa. And the outline of my talk is I will touch on Fermi-led observations. I will give a model overview of different models that we use to describe pulsars. I will focus on some salient trends that we believe are unanimously agreed upon. And then I will talk about binary systems, so-called spiders, redbacks, and black widows. And I will also touch on nicer and multipolar B fields, but not too much because I know there's a talk by Bogdanov and other people, I think Ray, that also will touch on this. And then I will also touch on TeV pulse emission from pulsars, a relatively new development in our field. And I will end off with some open questions. Now, Fermi-led, or Large Area Telescope, has brought about a revolution in pulsar science. Prior to Fermi, only 7 gamma ray pulsars were detected. And currently, we are now sitting at 250 detections. 118 of those are millisecond pulsars. So on the right-hand side, you can see a very nice plot by Patrizia Caravaggio. On the x-axis, you have the timeline. And then in the 70s, you'll see that we had SAS2 and COSB in the 80s and IGRIT in the 90s and so on, Algilay. And every time there's more photons, so the statistics are improving. And this is an example of the Vela light curve. And one can see how this builds up with more and more statistics. One can actually see the beautiful structure of the two main peaks as well as a third peak called P3. And this just encapsulates the revolution brought about by more statistics, more discoveries by Fermi-led. Now, the Fermi collaboration is working on the third pulsar catalog. It will include timing solutions, pulse profiles, spectra, and ancillary data for 250 pulsars. And this is an improvement upon one PC, which contained 46 pulsars, and two PC containing 117 pulsars. And one will see the general population characteristics of pulsars discussed in this catalog. Now, this catalog will also contain very gamma ray faint radio pulsars, as well as radio eclipsing binary millisecond gamma ray pulsars, or the spiders. And the lowest non-recycled pulsar has an E dot of 8e32 erg per second, which is very, very low in pulsar terms. Now, this catalog will aid in hunting for new and interesting pulsars. It will also enable population synthesis modeling that combines spatial distributions, evolutionary history of pulsars, and the average emission characteristics of pulsars. On the right, you will see, for example, the L gamma versus E dot plot, and one can see and appreciate that there's, for the millisecond pulsars in red, there's a different type of trend than the trend seen in the younger pulsars, the greenish ones. And so there's a turnover in the type of conversion efficiency that one would expect for these pulsars. And this will just be populated even more in the 3PC plot that will also contain these data and double the data or more. Now let me give a model overview. I will talk about additional models, force-free and dissipative MHD models. I will touch on striped wind models, kinetic or peak models, particle in cell, and also separatrix current sheet models. Now, traditionally, we had the polar cap, outer gap, slot gap, and the TPC two-pole caustic geometry type of models. These are more local models, and they invoke charge-depleted gaps in different places within the magnetosphere of the pulsar. In these gaps, we have acceleration of particles to relativistic energies by an unscreened electric field, parallel to the local magnetic field structure. And we believe that radio emission comes from a hollow cone close to the polar cap surface, and the GeV emission is believed to originate from curvature radiation. These models could give one spectra and light curves from first principles. Of course, these are local models, and one needs to take into account the microphysics of pair formation and the global current closure and those type of things. So there's been updates to this, but let me just show an example of the geometric modeling we did using a TPC and an OG model in the panel A and panel B there. And one can see for the millisecond pulsar J0030 plus 0451 that one could find actually quite good light curves in terms of the geometry of the TPC and OG. So maybe some of this encapsulates a bit of truth that will be carried over into the more sophisticated models later on. Now, the force-free models are those that solve Maxwell's equations, and for a plasma-filled magnetosphere, that's a limiting case, and there's no actual electric field that can accelerate particles. But still, this case is producing magnetic fields that are more realistic than the vacuum case, and they can be used as a basis for a model. Also, one step further is to have a dissipative model where there are still regions in space where there's a macroscopic conductivity that is not infinite, but rather it is finite. It might be high still, but it might be finite. And in these regions, one would have dissipation. And these types of MHD models provide also a further step in our modeling. And these models can produce spectra and light curves depending on whether you use it geometrically or physically. And this is just an example by Galapagos, where they modeled using FIDO, which is a new version of the dissipative models, where you have force-free inside, conditions inside, but outside the light cylinder, you have dissipative regions in the current sheet region. And they fitted a peak separation versus radial lag distribution of pulsars as measured by Fermi. And from their modeling, they could actually reproduce those types of constraints or this trend, and therefore this is quite promising to pursue. Now we also have striped wind models where the dissipation is in the current sheet beyond the light cylinder, where the co-rotation speed equals the speed of light. And these types of models ignore the details inside the light cylinder. They invoke synchrotron and inverse Compton or SSC inside of the current sheet. And you can see from the picture that if we have an inclined pulsar, then actually this current sheet is not flat, but it's undulating and looks like a ballerina skirt. And from this region in space surrounding the pulsar, one can actually expect 1 or 2 pulses per period for the light curves. But there remains a problem of scales because one can solve analytically even the bigger scale structure, geometrically speaking, but then the microphysics and magnetic reconnection and all these details of acceleration escape description because it's a much, much smaller scale. This is an example by Petri of synchrotron emission from the current sheet for different injection spectra and different Doppler boosting. And one can see that there's quite a number of shapes that one can actually expect from this type of model for the light curves. And the kinetic models or particle in cell models, they treat particle trajectories and electromagnetic fields self-consistently. So they take into account feedback of the motion of charges onto the fields and the fields effect on the charge motion. So in some of these models, we have pair production and injection assumptions, well, basically in all of them. And in some of these, we have GR modifications. And some of these models actually invoke synchrotron emission from the current sheet and not curvature radiation for the GeV spectra explanation. And there's still an ongoing debate whether it is actually the traditional CR or maybe if it is SR or maybe if it is synchrocurvature. So this is ongoing research. This example from Galapagos 2018 shows lots of runs by their kinetic models predicting the cutoff in the GeV spectrum as a function of spin down, E dot, and there's also different magnetic inclinations, there's different injections of particles, and there's different beaming or zeta values. And therefore, one can see that there's a lot of scatter, and one can actually find optimal models that correspond to data. Mostly, if one actually looks at the gray dots, those are from the Fermi catalog for young and millisecond pulsars. And one can see that there's optimal parameters that would reproduce these types of energetics and also then the light curves for those pulsars. Lastly, let me talk about the separatrix models or model. So if one actually takes note of all these developments in the peak models and dissipative models, then one can put that back into a emission model and implement that, and then one would see that there's a particle acceleration in the current sheet where the GeV emission comes from, and then there's optical emission invoked lower down, and then the primary particles giving you the GeV emission can actually upscatter the synchrotron emission by the pairs, and that would lead to SEC, and in some cases detectable TV pulsations. I will get back to this in a later slide. From this model, one can then predict not only spectra, but also multi-wavelength light curves. And one can also see the first peak disappearing with energy in this case, as predicted by the model and as seen in the data. Now, some salient trends from the modeling. We believe that caustics are very fundamental to forming pulsations, detectable pulses. So caustics mean that you have bunching in phase of photons due to different effects, curvature of the field lines, special relativistic aberration effects, time of flight lag effects, and these lead to caustic formation. We have bunching of photons in phase, and therefore these create beams. And if an observer slices through a beam, then that observer would see a peak or double peaks. Also, we believe now there's consensus that there's dissipation happening in the current sheet. So the focus moves from the interior of the light cylinder more to the exterior of the light cylinder in the current sheet region, where the magnetic fields of opposite polarity come together, and there's this sheet of dissipation and probably magnetic reconnection happening there. Furthermore, there must be pair formation happening because of the large number of particles needed to give us the luminosities we see and the fluxes we see in photons. So there must be pair formation happening that can sustain the currents in the star magnetospheres. And then also the P1 over P2 effect versus energy, I can explain with a picture. This is an example for Vela. If one goes up in energy from bottom to top, one would see that the first peak disappears in relative intensity with respect to the second peak. And this seems to be a somewhat universal trend, maybe not totally universal. One might expect to find counterexamples, but this is quite universal, and the models need to be able to explain this as well to understand the physics and the geometry and the local dynamics. Let me say a word on radio emission. So although the pulsars have been discovered in the radio band, the radio emission mechanism has been a mystery for decades. People have invoked geometric models, for example, hollow cones and a core component, to describe multi-component light curves, for example, triple or 5-component light curves. And that's the work of Liner Manchester and Rankin and collaborators. There's also the effect of radio to frequency mapping, where if one sees the pulses at lower frequencies, then they would be wider and more separated. And the idea is that this radiation comes from higher up, and this indicates the flaring of magnetic field lines as the particles lose energy and radiate at lower energies and frequencies. Therefore, then they probe flaring field lines, and one sees this effect. There's also a different interpretation of birefringence of the plasma that one could invoke to explain this effect. So one can actually constrain the heights of the emission using different effects. This paper by Blaskovich shows that one can use a retardation effect and explain that the middle of the light curve and the middle of the steepest incline of the polarization angle um, curve, that offset will give a constraint on the emission height for the radio emission. Now, the radio emission is of a very high brightness temperature, and this implies a coherent process, which can result from pair cascades on the open field lines. These are the general features that people do agree upon, but there's still no consensus on the actual emission mechanism. People have studied bunching effects, collective effects of plasma, instabilities, and even major action, but there are arguments for and against many of these mechanisms. A very recent development has been the paper by Filipov et al., where they studied non-stationary and non-uniform pair cascades. And they found that this led to a superluminal electromagnetic wave that can actually be identified maybe as radio emission because it's in the right range of energy and time scales, etc., seem to work out. So this is very new and still under, I suppose, discussion by the community, but there might be a way to actually create the radio emission using plasma effects. And this derives directly from pair cascades, which we believe is a very important ingredient in pulsar physics. Now let me touch on spider binaries. These are black widows and redbacks and other types of a pulsar and the companion in close proximity with very tight orbital periods of less than 1 day. The pulsar has an intense wind and it heats the tidally locked companion and excites a wind from the companion or even ablates the companion. Flares may occur because of variable heating, and there might be a hot day side to the companion, as seen in the schematic on the right-hand side, where we have a shock forming between the two winds that are colliding, and the pulsar in this case is enveloped by the wind, while there's still the companion being in the same motion, same orbital motion around the pulsar. So from these binaries, we see X-ray modulation. There's an example of 1723, and you see single peaks, but mostly actually double peaks. And we believe this is from Doppler-boosted synchrotron emission from the shock structure. There's also a few claims of GeV modulation. And the question might be whether this is the same synchrotron emission component that gives us the X-ray double peaks or single peaks. And there's no expectations for TeV emission from these sources, as I will show in the next slide. So what we've done here was to model the binary system and the interbinary shock and the particle transport, and one can use the flaring states emission. There you'll see the Suzaku and XMM flaring states and the power laws of emission measured there, non-thermal emission, and one can fit this with an SR component, also with the Fermi data upper limits there, and the modulated emission by Fermi. The fit is not perfect, of course, but one can use the anchor of the SR data and to anchor your emission predictions for the TeV band, and then one can see that actually in some cases one expects HACE and definitely CTA to see some of these bounded binaries. One can also, by doing this, probe the wind content, the particle acceleration, and the shock geometry in these systems. Let me move to NICER multipolar fields. So NICER, there will be a talk on this. So I just want to mention very briefly that one of the goals of NICER is to precisely determine the mass and the radius of several MSPs, or millisecond pulsars, and two recent papers by Miller and Riley reported strong evidence for multipolar B fields via X-ray, light curve modeling, and GR ray tracing, etc. Now, this paper by Kalapotharakos and company shows that one can actually fit the X-rays and the gamma ray light curve and the implied hotspots on the polar cap surface, which is not antipodal at all and by any means, using an 11 parameter model that invokes a dipolar and a quadrupolar B field structure. And so by using different constraints from different wave bands, one can actually constrain the multipolar field and the way it is set up and the geometry of this field. Lastly, the question is whether one would expect TV pulse emission from millisecond pulsars specifically. In the separatrix model that I've mentioned before, there's a pair synchrotron and primary curvature or synchro curvature emission, and the particles responsible for the primary curvature emission can interact with the pair synchrotron photons and lead to SSC that can give you some component that might be visible in some cases for HES or for CTA. And this is mostly for younger pulsars with high E dots, high B fields, high energies for the particles, etc. But still, one would have to see what CTA can tell us about these things and whether it will see even millisecond pulsars with TV emission or not. So let me end off with open questions. There are many observational discoveries, and we will see quite a few new types of pulsars in 3PC by Fermi. Also now the multipolar fields by Neisser and other types of discoveries will lead us to even more diverse pulsar discoveries and types of pulsars that we can study. There's still questions about the radio emission mechanism, definitely, and even the GeV emission mechanism, whether it's SR or CR or synchro curvature, and from where it comes, etc. In the magnetosphere, there's the question of TV emission pulsations from millisecond pulsars or younger pulsars. There's still a lot of work to be done for the microphysics details of non-stationary and non-uniform pair formation to support the global currents needed to have a closed circuit in these pulsars. And the global models can also contribute, and one model can refine the assumptions of the other model, type of model in terms of, let's say, boundary conditions, etc. And then there's the question of what will CTA bring to the table. Hopefully we will see more pulsars and maybe even millisecond pulsars for CTA. Not sure. It depends on energetics and geometry and all these things, but who knows? So thanks for listening, and let me end off by saying thanks for the invitation and thank you for your audience.